Alright, so this is my second video in a series that I want to use to lay a foundation for motivation for statistics and why we should care about statistics, why anybody should want to learn them. And I'm going to start with comparing it to something where we don't typically need statistics, and that is in many areas of physics. Physics does use statistics, but in many areas of physics they don't. They don't need them. So, for example, what if I made the claim that when light is reflected off of a smooth surface like a mirror, it bounces off that surface with the same angle that it hit the surface? How could we test that claim? Well, one way would be with a laser reflected off of a mirror. You could do several things. You could take a picture of the laser beam and measure the two angles. You'd have to have a really strong laser so that you could see the beam, or some kind of fog to scatter the light along the way so you could see the beam. A simpler way would be to place a barrier on the other side of the mirror, exactly as far from the point of contact with the mirror as the tip of the laser itself, and then measure how far off the ground the laser is and how far up the wall the point that bounces off the mirror. If the angle of incidence and reflection are truly the same, the point on the wall will be exactly the same height as the laser. Physics and chemistry are full of these kinds of relationships. Newton's laws of motion, relativity, Boyle's law, many more, Einstein's theory of relativity, that don't require statistics. In fact, physicists are always in competition to see who can measure to one more decimal of precision. So never mind statistics, which is all about variability. No, they get exactly the same number every time they measure this stuff, and so much so that they're even trying to just get more and more decimal places to be more precise with their measurements. But what if the surface isn't smooth, and the position of the laser isn't known exactly, and we wanted to predict where the laser would go after it struck this rough surface? Well, now we can't predict precisely because we don't know enough. But we could instead shoot lots of lasers from lots of different angles and heights and come up with a set of probabilities. Where is the laser probably going to go? Now we need statistics. And in fact, there's lots of areas in physics where they need statistics too. Well, I'll get into causality in another video. Think about that ultimate example of something that requires statistics: a coin toss. Every probability class starts with examples of things like coin tosses, dice rolls, and card selections. But doesn't the coin follow the same laws of physics as laser beams? Well, yes and no. Not the same laws, since lasers follow laws related to light, but coins are subject to all of Newton's laws of motion. In fact, we could easily build a coin tossing machine, and engineering students probably have, lots of times, that produces exactly the same result every time. The reason coin tosses are essentially random is that the human coin flipper is not like a machine and cannot control the exact forces put on the coin to make it come up the same way or any desired way every time. Also, a really good toss goes high up in the air, and random air currents can influence it, other things. If we could know all of the starting conditions, all of the forces that acted on the coin right at the beginning, and how the coin was oriented and so forth, we could predict the outcome of a coin toss with physics instead of statistics. But knowing all that stuff would be super expensive, possibly even impossible to know in enough detail to predict the outcome of a fair coin toss. So in statistics, words like random and probability get tossed around a lot, and we'll go into formal definitions of those things in future videos. But for now, I can just rely on your intuitive idea of what random means. You probably think it means something like unpredictable, could be heads or tails, and nobody can know. But that's actually sometimes true. In quantum mechanics, which I do not pretend to understand, there is an idea of randomness that is really random, an idea that some things are fundamentally unknowable and unpredictable, like where an electron will hit a phosphor screen when it has to go through a slit in a metal plate first. That's a very deep kind of randomness. Some people say that the exact location of impact is fundamentally not caused by anything. It does follow a pattern. In fact, what it follows is a probability distribution. But on any given trial, the place the electron will hit is completely unknowable until it hits. But the randomness we deal with in biological, social, and medical sciences is actually not that deep. It really means having lots of causes, not having no causes. Having lots of causes, not all of which can be measured, or at least measured easily, and so fundamentally caused by lots of things, but practically unpredictable even if we measure those things. So that's what we mean by random. Just to take an example from sports, will the batter hit the next pitch? Nothing about this situation is mysterious to physics and biology. What is unknown in any given instance is the exact state of each muscle and neuron in the pitcher's and batter's body that will contribute to the pitch and the eventual swing, along with tiny contributions from wind, heat, moisture, and so on that might ever so slightly alter the ball's trajectory. Mental factors, which are ultimately neural factors, such as alertness, attention, motor skill, fatigue, in both the pitcher and the batter, all come into play. But that's so many causes, each one acting perfectly in line with the laws of physics, but all unknown at the instant of the pitch, that whether the batter will hit is practically unpredictable right up to the moment the bat does or does not make contact with the ball. What we can do is use statistics to figure out who the best hitters and pitchers are, what circumstances favor or disfavor them, and so on, and make educated guesses. In some fields, those educated guesses are wrong just as often as they're right, but in many fields now, after years of research, those guesses, which we typically call predictions or forecasts — I'll talk about the difference between a prediction and a forecast in a future video — those guesses are actually right more often than not. But that's a topic for a future video. Hopefully now you have a better understanding of why we need statistics and not just precise mathematical equations that predict perfectly every time.